Hello everyone, in this video we're going to look at how to find the volumes of solids of revolution by rotating the region between two curves about y-axis. Now you can see on the left hand side I got two curves. One is you got g of y and then another one is f of y. And you got the boundaries for the y starting from C to D, and you're rotating about the y-axis. And when you rotate it, you pretty much get this kind of shape. And remember, the middle part is actually hollow. Now, again, we're going to use the disc method here. We just slice it, and sometimes we actually call it washer because once you cut it off, because it looks like a ring, so we call it washer. But still, it's actually the same as a disc method. Now, let's find the volume of one slice. So the cross section is the big circle area minus the small circle area. And the big circle's radius is represented by the horizontal length from the y-axis to the edge of the right-hand side curve. So this is f of y. So I can say it is pi, factorize it out, r1 squared, which is f of y squared, minus the inner circle radius is starting from the same point to the left-hand side curve, which is represented by the g of y. So minus g of y squared. So that's the cross section. So all you need to do is times by the depth of the cylinder. So the depth of the cylinder is actually the change in y value. So therefore, I can say the volume of the entire solid with the hollow part in the middle is integration of C to D, the range of the y that is given that create the region, and you have pi bracket f of y squared minus g of y squared times by the delta y. We use dy. This is the volume of the solid of revolution when you're rotating the region between two curves about the y-axis. Let's have a look at this example here. Find the volume of the solid generated when the region enclosed by these two functions and they have given the restriction for y is revolved about the y-axis. So let's quickly draw the picture. Y equal to cube root of x. I'm just going to draw the curve that is on the right-hand side of the x-axis. And then you have y equal to x on 4. That's just a straight line. Okay. And this is 2, and this is 0. Now, we rotate this one about the y-axis, and that will give us something look like this. Okay, so there is actually a hollow part in the middle. You can see the ring will be created. Okay, now let's find the volume. So imagine you cut the slice horizontally, so you will have a cylindrical ring like this. So the entire volume of the solid is integration of from 0 to 2. The cross section is pi r squared, the outer circle area minus the inner circle, and we can factorize the pi out. And so the large circle's radius is from the center to the right-hand side curve edge. Okay, so this is actually represented by the x of the y equal to cube x. So we're going to rewrite it, both function in terms of x. So this will give us x equals to y cubed. And then y equal to x on 4. If you rewrite it, x equals to 4y. Now, if you pay attention, the straight line is on the right-hand side, so we say that is the outer circle. So therefore, the radius for the outer circle is 4y, and the radius for the inner circle is y cubed. So therefore, we have 4y squared minus y cubed squared, and the depth is represented by change in value of y, so it's delta y, so we write it dy. Now we just need to integrate it, take the pi out and integrate this part, and that will give us 16, because when you expand it, it's 16y squared, and you have y to the power of 6. So I'm just going to write it here, minus y to the power of 6. So if you integrate it, so it's 16y cubed on 3 minus y to the power of 7 on 7. And the boundary is from 0 to 2. Now you need to do the substitution. So upper boundary first. So you have 16 times by 2 cubed on 3 minus 2 to the power of 7 on 7. And minus the substitution of 0, and that will give you 0. So therefore the final answer is 512 pi on 21 unit cubed.